Hello! Today I want to talk to you about geometric reasoning. Specifically what I want to talk about is called deductive reasoning, which is we're going to build an argument that shows that something is true using what's called valid reasoning, or making valid conclusions from the information that is given. So to talk about this, we need to know what a conditional statement is. Okay, a conditional statement in geometry is in the form if something, then something, right? So it might look like, if it rains, then the picnic will be canceled. Okay, and so each piece of this has a sort of definition that we're going to use to talk about it. Okay, so we have a hypothesis or a premise followed by a logical conclusion. So these things have a logical order, right? And typically the word after, or the sentence after if, is our hypothesis or premise, and then the sentence after then is going to be our conclusion that sort of follows from that premise. So in this example, if it rains, the picnic will be canceled. Our hypothesis is it rains, and our conclusion is the picnic will be canceled because it follows logically, right? If it rains, we're going to get all muddy, it's going to be gross, probably cold, right? We don't want to hold a picnic in those conditions. So that's sort of how these work. And so just to help you understand, here's a couple examples, right? The first one, if a polygon has 6 sides, then it is a hexagon. Okay, a polygon has 6 sides would be our hypothesis. That comes right after if, and then it is a hexagon is our conclusion. That comes after the then. Right. Pretty straightforward. Okay, but it doesn't always have to be that way, right? So if you look at our second sentence here, another performance will be scheduled if the first one is sold out. Right, so in this case, they've kind of flipped the order on us. But we see that right after the word if, the first one is sold out. That's sort of our premise. And then we don't use the word then, but what follows is that another performance will be scheduled. That makes sense, right? If the first one sold out, we're going to schedule another one for those people that didn't get to see the first one. Okay, and then in this last one, we're not even explicitly using if or then anywhere. It's sort of implied, right? A quadrilateral with 2 sets of parallel sides is a parallelogram. Our hypothesis would be a quadrilateral with 2 sets of parallel sides. And our conclusion is, well, then that is a parallelogram. Okay, so that's generally what conditional statements are. All right, and we have a shorthand that we can use to sort of write this down, because in geometry we end up writing these sentences a lot, and so since we don't want to have to keep rewriting the same words over and over, we can abbreviate each sentence with a P or a Q or just some random letter. It's just a way to write this without having to rewrite everything over and over and over. So instead of if it rains, the picnic will be canceled, we can just say if P, then Q, knowing that P stands for that hypothesis, Q is our conclusion. Okay, so this is just another way of writing that, so you can see where this is coming from.
So our law of detachment is our first of 2 laws relating to deductive reasoning. And so in order to talk about this, we need to talk about our system. So Euclidean geometry, or basically what you're learning if you're learning geometry in the US, is our system that's built on postulates and theorems, right? And so the postulates are just sort of the rules we take for true without a proof, meaning it's the assumptions that were necessary to make in order to build this system. Okay, and then the theorems are rules that are shown to be true by proving them, using the postulates, using properties, using math facts and definitions and things like that. Okay, and most of these theorems and postulates are written in the form of a conditional statement. For example, the congruent supplement theorem states, if 2 angles are supplementary to the same angle, then the 2 angles are congruent, right? Right there, we have a conditional statement. If 2 supplements of the same angle, or 2 angles are supplements of the same angle, that's our hypothesis. The conclusion is those 2 angles are congruent. Okay, so now what the law of detachment actually says is that if I have a conditional statement that's true, which all of our theorems and postulates are true, and the hypothesis is met, then the conclusion must be true. Okay, so first I'm going to do a silly example, and then we'll do a real one. Okay, so if a car is out of gas, then it will not run. So let's say we've got that conditional statement, and it's true, we're told it's true. Okay, our hypothesis is a car is out of gas. The conclusion is it will not run. Furthermore, we are then given Mr. Moser's car is out of gas. So a valid conclusion we could make, because we've met our hypothesis, is that the car therefore will not run. That is a valid conclusion. because we've met that, the law of detachment says that the car is not going to run if it's out of gas. Okay, that seems maybe pretty obvious or straightforward, but here's where it gets a little bit sticky. Okay, so let's use the same conditional, but instead you're told Mr. Moser's car will not run. So we're given that Mr. Moser's car will not run. We've got this conditional statement. We have not actually met the hypothesis in this case. Okay, and so a lot of times we jump to, because of what's written here, we'll say, well, it won't run because it's out of gas. And that's sort of the reasoning we make, but we haven't met the law of detachment. We've not met our hypothesis here. And so this is actually not true. And we can show that with what's called a counterexample. I can say, right, well, the battery could be dead on my car. The spark plugs could be missing. Maybe I parked my car at the bottom of a lake. Right? That's a little bit hyperbolic, but I'm trying to make the point here is that we can't make that leap in logic. We don't know the reason that the car will not run without more information. So it might be possible to get more information, but right now we don't have enough to say that the car's out of gas. So that's what the law of detachment, that's how it works. All right. So that would not be a valid conclusion to say that it's out of gas. We would need more information. Now let's relate that to actual geometry. Okay. So using the supplement theorem, which says if two angles form a linear pair, then they are supplementary. All right, and we're given angles AOC and angle BOC are supplementary. Okay, is it a valid conclusion to say that they form a linear pair? Well, let's think about this for a second. Have we met the hypothesis? Do we have two angles that form a linear pair? That's not given here. We're only told that they are supplementary. And so what could be the case is that angle BOC and angle AOC are not a linear pair, but they are supplementary. So it would not be a valid conclusion to say that they form a linear pair without more information, right? We haven't met that hypothesis, so the conclusion that they form a linear pair does not work. All right, but if we're given that angle AOC and angle BOC form a linear pair, in that case we've met the hypothesis, and so the conclusion that they are supplementary, that is they add to 180, is going to be true. Okay, so if I've got AOC and BOC, this is our linear pair, we don't know what these measures are, but we know they're going to add to that 180. Okay, and so our second law for deductive reasoning is called the law of syllogism. All right, and all that is it says if we have a conclusion of a conditional statement that's true, and it matches the hypothesis of another conditional statement that's true, we can make this third conditional statement in which we use the hypothesis from the first statement and the conclusion from the second. Okay, that sounds a little abstract. Let's use an actual example. Okay, so going back to the it rains thing, right? So if it rains, then the picnic will be canceled. So now let's introduce the second conditional statement. If the picnic is canceled, then I will read a book. So the law of syllogism basically just says we can make this new conditional statement that says if it rains, then I will read a book. Okay, and so I'm using kind of the color highlights here to show you where that's coming from, right? Because these two are the same, we can make this new statement. And that means, given certain information, we could make a valid conclusion here. All right, so let's take a look, right? If we meet that, right, so given it rains, we are actually meeting the hypothesis of two conditional statements. Right, the first one, if it rains, then the picnic will be canceled. And then the second one is that new one we just made. If it rains, then I will read a book. So since I'm given it rains, I can actually make two valid conclusions. First is that I will read a book, and the second is that the picnic will be canceled. All right, and so this is kind of putting together the law of syllogism and the law of detachment into one sort of thing, right? Just by meeting this one hypothesis that's shared by multiple different conditional statements. Okay, so now again, let's relate that back to our geometry and to our theorems, right? So the supplement theorem, remember, was if two angles form a linear pair, then they are supplementary. Okay, and then the definition of supplementary angles is that they're 180 when we add them together. Okay, and so I wrote this as a conditional statement to kind of show that, right? If two angles are supplementary, then their measures add to 180 degrees. And so now notice here, the conclusion of the first statement, they are supplementary, matches the hypothesis of the second, if two angles are supplementary. Right, they're not written exactly the same, but this is where we kind of use that ELA skills. Okay, and so that means what we can say then is, by the law of syllogism, if two angles form a linear pair, then their measures add to 180 degrees. Great. Okay, so what can we do with this information? We've built this valid argument. All right, so let's put all this together. So if I'm given this diagram, this triangle ABD, and we're given these measures, and we're asked to prove that the measure of angle ACB is 77 degrees, well, if I can look at this diagram and recognize right here, I have a pair of angles that form a linear pair, ACB and DCB, that can set off the same chain of thinking we just saw on the last slide. Okay, if two angles form a linear pair, then they're supplementary. If two angles are supplementary, then their measures add to 180 degrees, right? Which we can then think of as just this new sort of conditional statement here. All right, and that means if I want to go on my way towards proving this statement here, what I can do as a starting point is say that these two angles that form the linear pair add up to 180 degrees, right? The measure of ACB plus the measure of DCB is 180. Okay, and then from there we can start to substitute in values. We can solve using algebraic properties, and then get to our proof statement from there. But this is sort of the thinking we use to build those arguments. And as you learn more and more theorems, as you learn more and more definitions, right, those chains of thinking become more and more complex. We can start to recognize many things at once and put together these logical arguments. So that's my video. I hope you liked it. Thanks for watching. If there's anything that you want to know more about, or you want me to kind of dive in deeper, or you just want to comment on this video and let me know what you think, go ahead and do that. I'd be happy to hear from you. So thank you for watching and have a good one.